Welcome to the North American IPv6 Summit 2015. Thank you for joining us here in person in Denver, Colorado, and from around the world on the virtual platform. We actually have people joining us from Europe and from Africa. My name is Augie Mitev. I'm the chair of the Rocky Mountain IPv6 Task Force. This is our 8th annual event. The theme for this year is putting IPv6 to work. Special thank you to the Rocky Mountain IPv6 Task Force and to the California IPv6 Task Force for putting this event together. One person I would like to recognize above all is Dan Torbett. Dan did a great job working with all the speakers building this program for today and tomorrow. Dan, could you please stand up? This event is being recorded. All recorded sessions and the updated presentations will be available on the virtual platform before May 1st. You can all access the virtual platform here in this room. You all received an email message, registration confirmation last week. In that email message, you will find the URL and the login information for the virtual platform. The wireless network is up and running. We're broadcasting SSID, NA, IPv6 via OS Dual. And the WPA key is IPv6 is best IP. Please take time to visit our exhibitors. Without their kind sponsorship, we would not have this event. A lunch will be served in this room to your right, and then we have beverages in this room to your left. The beer and gear reception will start after the last session today around 4:30. The beer and gear reception sponsor is BT Diamond. Thank you. We're giving away prizes, books, and items tomorrow at noon. For those of you that register for the certification program that's scheduled for actually today at 2:30, 2 o'clock in the afternoon in room 4, which is on your left, just behind this wall. And finally, enjoy your time with us in the next 2 days. Thank you. Our keynote for today is Jeff Doyle. Jeff specializes in IP routing protocols, SDN, data center fabrics, MPLS, and IPv6. Jeff built, designed, and helped build large-scale carrier networks around the world. He worked with early adopters of IPv6 in countries like Japan, China, and South Korea, and many other carriers around the world. Jeff is the author of numerous books, including CCI Professional Development, Routing TCP Volume 1 and 2, and quite recently a book on OpenFlow. Jeff is also the co-founder of the Rocky Mountain IPv6 Task Force. Welcome, Jeff.
Where to go? Just go back to the presentation. Are we up? There we go. Good morning. I chose this topic, IPv6 and SDN, in part, at least the seed idea for it came from the fact that a lot of the same organizers of this event that have been doing this for years with IPv6 also have begun organizing an SDN event mostly through the Colorado Internet Society, a little bit later in the year. We did one last year. We'll probably do one again this year. And I thought, well, it makes kind of a nice, interesting meld of topics to talk about IPv6 and SDN and maybe a couple of other things, all in the same context. And the interesting part is, well, why am I referring to IPv6 and SDN and other scary things? And the real reason for that is that the media loves to talk, the industry media loves to talk about disruptive technologies. It's one of those buzzwords that's out there. But as a network operator, do you really want to hear the word disruptive? What does that conjure up for you? It's the idea of things stop working or things are distorted. There's a few definitions that I pulled just out of the dictionary here, to interrupt processes and so forth. That's not really what you want to hear in any new technology. Here, have this. This is disruptive. And of course, that's not really what the media means. They're really looking at the industry itself and how technologies are going to change the way the industry works, the way products are going to be presented to you, and so forth. But what I want to focus on is really what these things mean to you and your networks as network operators. And so the first question is, well, what kinds of things really haunt network operators? What do they worry about, and stay up at night thinking about? Well, right at the top of the list is human error in networks. Depending on the study you look at, anywhere from 60% up to maybe 75% of network outages tend to be mistakes that are made by humans. You configure something wrong. You don't follow necessary policies and procedures. You simply, fat finger something on the CLI, and things go down. And of course it can get a lot worse than that. That's sort of the classic huge mistake that have brought down fairly large service provider networks in the past are things like, accidentally redistributing full internet routes into OSPF tables. And you get this network-wide meltdown that not only takes the network down, but is very difficult to recover from. You have to sort of shut down very systematically different parts of your network to start bringing things back up. So, human error, big problem for resiliency and uptime in your network. Poor visibility is certainly a concern. One of the things right now, I'm very involved with data center networks right now, and modern data center networks, especially if you're doing distributed applications like high performance compute and Hadoop and things like that, tend to create a lot of east-west traffic within data centers. And data centers, at least the security models, tend to still be built a lot on north-south traffic, what's going in and out of your data center. And those tend to be the areas that are secured, but you have very little visibility into that majority traffic, which can be up to 80% of data center traffic that's going east and west across your data center. Even in service provider networks and enterprise networks and so forth, having a good view of what's going on in your network is essential. Without that, you can't really do any kind of good, accurate capacity planning. You can't get a good understanding of where your traffic patterns are. And related to that is security. If you can't see what's going on in your network, it becomes very hard to secure what's going on in your network. So visibility becomes tremendously important. Unpredictability. This goes into the same thing with visibility. How well can you predict where your traffic patterns are going to flow in your network? When you set a policy, what's that going to do? And if you engineer your traffic patterns, how's it going to affect other parts of the traffic patterns in your network? That becomes important. Inconsistency. do you get the same kinds of qualities of service and qualities of experience and traffic patterns and capacities in one part of your network as you do in the other? Again, this becomes very important in data center networks, but it's also important in enterprise and service provider networks. Unreliability, how well can you, how deterministic is your traffic in your network? Unavailability, I don't think I have to say much more about that. Scalability is a huge topic, and what that means there, and this applies not just to data centers, but to all kinds of networks, how well can you grow your network without having to change the gear in your network? How well can your network scale out without having to scale up? What everybody hates to do is have rip and replace projects where, okay, I'm moving to the next stage in capacity in my network, I'm rolling out new applications, very demanding applications. What you don't want to have happen as you do that is have to pull out one type of network gear and put in another type of network gear just to support that new capability. And then finally, just CapEx and OpEx. It's what everybody is concerned about. OpEx really even more than CapEx. That tends in most networks to be the larger expense. It's also the more difficult thing to really measure. I mean, you can just look at budgets for OpEx, but trying to set metrics that really determine, well, what's influencing my OpEx budget becomes very difficult and a bit obscure. CapEx is pretty easy. You know what you're spending, you know what you're spending it on. It's pretty easy to see what the factors are determining OpEx. So kind of putting on maybe not so much my psychic hat here, if you just look at what's going on in networks right now and where the trends are going, you can get a pretty good idea of what's going to be happening in the near future with networks. One of the things that I'll say right up front is that eventually we have to be using IPv6 only networks. What's really behind that is nobody likes the idea of having to operate two different protocols in your network. And we can't really go back to IPv4. I don't think that I have no idea if other presentations in this will start talking about why IPv4 is depleted, but I don't think that you really have to convince anybody about that anymore. We all know that IPv6 for most of the regional internet registries is depleted. It's very hard to get public IPv4. Did I say IPv6? IPv4 addresses anymore. IPv6 is really the only path forward, and I'm going to be talking quite a bit about why that's essential for us. And I've looked at some of the other things on the agenda, and I know a lot of other people are going to be talking about that also. So there's going to be some tipping point at which IPv6 traffic has grown enough that people are going to consciously and very decisively start trying to push IPv4 out of their network, simply to simplify things and to get to the point where you're back to only running one protocol. Things are going to be automated and programmable. Those two things don't necessarily mean the same thing, but you can get automation now. We've been moving to automation in different ways for years. We've written scripts for our network to make things easier. All of those everyday routine tasks that we do in the network. Anytime we do a major reconfiguration of our network, we try to script things so that it's automated. That goes into reducing human error. But what programmable is really saying is we want to start getting human beings out of the direct change or the direct chain of how we change our networks and how we operate our networks. We want the human beings to sort of be off at the side, defining policies for our networks with, if then else kinds of languages, and then let the network adapt itself to those policies. We want things to be economically scalable. I talked about scalability in the last slide. As we grow our network, we want to be able to do that as inexpensively as possible. We don't want to, again, start having to do rip and replace kinds of projects. And then the last part is something I've been talking about for a while, is that we don't want just software-defined networks. What the trend is really going toward, and what SDN is a part of, is getting to the point where we have application-defined networks, which basically means, again, human beings kind of get out of the way of that direct chain, and applications are telling the network, here's what I need, moment by moment, to run. And the network adapts to that. And there are a lot of trends right now. If you look at Cisco ACI, it's very much a trend in that direction of policy control in the network and adapting to the demands moment by moment of applications. So what I really want to talk about in this are three fundamental changes to the way we build networks. One of those is IPv6. The other is SDN. The last one that I want to talk about is bare metal hardware. That's something that is fairly new, and we're starting to see a lot of trends there. And with the little background I've got up here, you might be saying, well, aren't cloud networks a part of that? And I would contend, actually I would probably talk about clouds if I had a lot more time, but I would contend that clouds are really more of a service model and a deployment model for networks, whereas IPv6, SDN, bare metal networking, and things like that are basic building blocks of how we construct networks, including cloud networks. And I should say, I work for an SDN company right now, just as a disclaimer. And I'm not talking about these topics because I work for an SDN company. I actually work for an SDN company because I think these topics are important, and that's why I joined. So wanted to be sure and kind of get that perspective in there. So how far along are we? I've got this technology curve here that I stole somewhere off the internet because I was too lazy to draw my own, but everybody's is used to these technology adoption life cycles, and if you've read Jeffrey Moore's book about crossing the chasm, you've certainly seen all this and where all these things lie. So where are we with all of these technologies that I just talked about? Well, IPv6 for service providers, I think, and a lot of this is my opinion, but actually it's all my opinion, but I think we're pretty far along with IPv6 in service provider networks. You'll very seldom run across a service provider network nowadays that isn't pretty well along in IPv6 planning, if not, openly capable of providing IPv6 services. Service providers that are not there are probably going to have some business problems and expansion problems in the years to come. It's a little bit different for enterprises. Enterprises are still kind of in the early adopter phase. Enterprises tend to be still asking the kinds of questions now that service providers were asking maybe 8 years ago. Is it really true that I'm going to run out of IPv4 addresses? Can I make money some way? How do I get a return on investment with IPv6? When do I need to be doing this? And how do I do this? Those are all kind of questions that enterprises are still asking. And is there any way I can avoid IPv6? Because I don't want those expenses in those projects. So early on. SDN, much earlier than that. There are, if you look at some innovators like Google that have been running SDN in their networks for quite some time, they are out there. But even if you look at more mainstream SDN operators, There's some financial networks out there, large financial networks. There's some providers that are running SDN. There are a few very large service providers, in fact, that are examining SDN and experimenting with it. But it tends to all be still just evaluating, figuring out how to use it, figuring out how to get it into the network. Surprisingly, even though, maybe you've heard less about bare metal switching than you have about SDN, I actually think that's a little bit further along than SDN. So I want to start by talking about bare metal, then I'll talk about SDN, then I'll get back around to IPv6. So the first thing is to know is that bare metal is not a new concept. We've been building servers like this for years. Basically, you decide what silicon you want to use in your, there's certain choices. You decide what hardware you want to support. Above that, you decide what operating system you want to run on top of that hardware, and then you decide what applications you want to run. And probably that's going to be a top-down decision. You'll start by, what applications do I need to support with this server? And then from there, what's the best operating system to support those applications? Below that, what, probably is the most economical and best performing hardware for that particular application. And then finally down to, what kind of silicon best supports that. So, all this to say this is an old, not old, but several years old way of doing things, and we're used to it with the servers. The thing is, we're not really there with networking in most cases. And by the way, I'm not picking on Cisco here. This is just was a nice picture to put up there. But if you look at all of the large networking vendors that are building, sort of large vertically integrated systems, you don't have a lot of variability. You don't have a lot of choice in what you're getting with those systems. The silicon at the bottom can be custom ASICs, very proprietary. The operating system that runs is proprietary, and all the way up to the features. You wait for the features in there. And I should say that the trend here is, even within the large providers, is to start moving away from these kinds of very tightly, vertically integrated systems. They're still around, they'll be around for a long time, but if you look at the big providers, Cisco, Juniper, Brocade, Arista, they are starting to move into product lines that are built with merchant silicon. And it's an acknowledgement of what's happening in the bare metal kind of market. And one of the, I should say there's just kind of an anecdote here. I worked for one of the large providers, Juniper, back in, I worked for them for about 10 years, starting about 1997. And one of the things I noticed with Juniper was, and I asked early on, was, really what we focus a lot of our marketing around is the operating system, our software. Anybody can, it seems like, can build good high-performance hardware. Why don't we just market our operating system to anybody that wants to load it? And, that was kind of a naive question at the time. I certainly didn't have any vision into what was going on in the future. It was just a question I asked. The answer I got back at the time is, well, that just won't work because we're very tightly integrated into our ASICs, and into the features that are there. You've got to have this hardware that supports that software. You can't just port it to anything you want. Well, that's kind of, as it turns out, where the trend is going now. And there's an interesting cautionary tale for companies that continue to be oriented to very proprietary hardware, and that's Sun Microsystems. It wasn't that many years ago when you built a data center, Sun servers were pretty much the gold standard for building your data center servers. That was the way you did it. Where they made a mistake was they tended to be very hardware oriented, and they were very much integrated. And if you look at between November 2007 and November 2008, they actually dropped. This was with the advent of people like Dell coming along with open servers and x86 based hardware, and Sun dropped about 80% in value in a very, very short amount of time. And Scott McNeely, the CEO at the time, actually acknowledged, if we had decoupled from our hardware more and become more of a software-only kind of company, Solaris would have been a much larger operating system and more popular operating system than it ended up being. So here's where bare metal comes in. If you look at open switches and you look at the way we've built servers, well, this all looks very familiar. Just like with servers, we have an open architecture. You have vendor choice at multiple levels. You can innovate very quickly, and you have a very low cost, total cost of ownership with these. There are a bunch of companies you can choose among for merchant silicon. There are multiple boxes that can run that silicon. Some of these are brand name companies. Some of them, you can go directly to the manufacturer. Interestingly enough, if you look at people like Quanta and Acton, they will sell you switches, or they'll sell switches to larger vendors called white box, where the vendors themselves, it's the same switch, it's the same silicon. You get like a Broadcom Trident 2 chip in there, but they're putting, the vendors are just putting their own labels on the front of those switches. So you can actually get the same switches at bare metal pricing sometimes. You choose the operating system you want on top of that, and you choose features you want on top of that operating system. So that's bare metal. Question is, and this is something that always comes up, is, well, if I'm moving to bare metal, does that mean I have to build my own? Do I have to have the engineering expertise to manage these switches, to build the operating system on top of it, and so forth? And some of this comes out of what you're seeing right now with Facebook. Google has been building their own switches for quite a while. Facebook is building their own switches. You've seen that in the last few months with Wedge and with Sixpack and that sort of thing. And the answer is no, you don't. And that's really where SDN and open operating systems come in, which is the next piece of all this. But some of the things to be aware of right now is that, according to Infinetics, bare metal actually accounted for 11% of all data center ports shipped worldwide in 2014, and according to them, by 2019 is going to be 25% of all data center ports shipped. Last week, I sat through a presentation by Alan Weckel at Del Oro Group, and he said, Google is creating their own switches, building their own switches internally, and if you were to actually consider them a vendor of Ethernet switches, even though they are their own customer and they're the only customer, they would actually be the second largest switch vendor after Cisco, which is pretty interesting. There's another Del Oro observation that I saw just a couple of days ago that says that in 2014, by overall budgetary spend, 7% of budget spend is on open or bare metal switches. When you extend that to the budgetary savings, the Capex savings on bare metal switches, that means that about 25% in 2014 of Ethernet ports sold were bare metal. It's an interesting perspective. So where bare metal really comes in, and the real significance of it is in Capex and what you can save on Capex. These are a couple of different websites, commercial websites that I pulled up just in I did this just last week, searching around, and you can actually see over here on the left, there's an Acton switch, kind of a top-of-the-rack data center switch with 48 10 gig ports and 4 40 gig uplinks. You can get that for a little under $6,000 right now. For kind of a spine switch in the data center, you can get a 32-port 40 gig switch for about $7,500, which comes out to about $234 per 40 gig port. Doing a bit of comparison shopping, if you look at some comparable products, Arista has a 48-port 10 gig switch with 6 40 gig uplinks that runs a little under $30,000. Juniper's QFX 5100 runs about $28,000, which for 24 40 gig ports. So that's about $1,200 per 40 gig port. Cisco's Nexus 3132 with 32 40 gig ports, same as up here, is about $48,000. So there's some interesting economics there. Part of what's not there is, of course, you're getting an operating system, you're getting maybe support. Certainly you're getting support. You're also probably going to get some discounts, fairly sharp discounts, with these vendors that you would not get if you're just buying bare metal right out of off the internet. So, those are things to take into account, but it still shows you a large contrast in what you can get. And there's a good paper out there by Cumulus Networks that actually looks at the economics of building an entire data center with bare metal as opposed to a couple of large vendors and some pretty significant Capex savings. So bottom line there is that what matters with bare metal is Capex savings. Bare metal doesn't really give you anything as far as OpEx savings. And in fact, if you try using bare metal by itself, your OpEx is actually going to go way up because there's obviously a lot more support that you have to do, a lot more engineering around operating systems with bare metal than you would if you're buying the single integrated system off the shelf. So that's really where SDN comes in, software-defined networking. And, the first question is, well, what is SDN? If you look, and I've found that even though we've been talking about SDN for a couple of years now in the industry, when I have one-on-one discussions with customers, they tend to still be a little uncomfortable about what that definition is. What are we really talking about with SDN? I'm hearing all these acronyms, and I've thrown as many as I could think of up here. Some of them are directly related to SDN. Some of them are only loosely connected to SDN. Some of them have absolutely nothing to do with SDN, but still tend to be mentioned in the same conversations. And so people, are kind of saying, and then of course you get marketing in the middle of everything, and you've got software-defined security and software-defined storage and software-defined data centers and software-defined X. So what is it? I have a couple of definitions to try to simplify all of this. The first one is what most people think of when you think of SDN, which is that SDN is a layer 2 or layer 3 architecture in which a centralized controller controls the forwarding behavior of a set of distributed switches. And by switches, I should say, those may be layer 2 switches, they may be layer 3 switches, maybe routers. We have really for the last 20 years have been building routers and switches that separate the control and forwarding plane, control and data plane, if you will, within the single switch. And there's certain advantages to that. You get better performance in the data plane, you get independence from the control plane. Control plane getting busy doesn't affect forwarding and so forth. Busy forwarding doesn't affect the control plane. SDN in this concept just takes that a little bit further and says, well, rather than having just that control plane separation in a single device, we're going to pull it completely out of the device. And so our distributed network are just forwarding planes. We are going to centralize the control and update from there. Still doing the exact same things, we're just doing it from a centralized location. And this is where this definition starts becoming a little more vague. If you have a centralized controller, you have a centralized point of failure. So, you want to start building redundant controllers for your network. You also, if you're spread out, you want to start building hierarchies of controllers. So it's a little more complex than just saying we're going to have a centralized controller that's going to run all of the forwarding planes in the network. And that comes to a definition that is maybe not as easy to follow, but is actually more accurate, which is SDN is a conceptual framework in which networks are treated as abstractions and are controlled programmatically with minimal direct touch of individual network components. There's that human factor in there. The more you can have humans not having to touch every individual device, the less mistakes you have, the easier it is to control your network. So you're controlling the network from one centralized place, and you're doing it programmatically. The network itself, and this is actually important, from the SDN perspective, becomes an abstraction. It becomes a model in the SDN framework that you're working on, and then SDN can push down the policies into the actual components of that model as you work out your policies. There are some good things about the integrated switches that we use right now. If you think about, in any redundant chassis type of switch, we have supervisor engines or, routing engines, whatever the vendor is going to call those. We have line cards, and they're connected by some kind of backplane. If you think about the way you work with those, you don't log into the backplane, you don't log into line cards. You run everything from the supervisor. There is actually an operating system on the line cards. There's microcode that gets loaded down there, but you don't have to directly touch that operating system. You do it all through the supervisor. If you look at, in this case, this is a data center network, but if you look at how we build things with an SDN network and small switches now, what we have here is sort of a very simple leaf and spine topology. A lot of times it's called a cluster topology. It's non-blocking, has very low oversubscription, and it's all controlled from the SDN controllers. You don't actually have to touch these switches. And here's how everything sort of works together. The SDN controllers are like the supervisor in a chassis. The spine switches are like the backplane. And the leaf switches or top of rack switches are like line cards. Again, this kind of shift is happening in data centers, but it's applicable also to enterprises. It's applicable to service provider networks. The same things that we're learning there are already starting to move out into those other arenas. So why does it matter? Well, if you look at putting individual control planes on a distributed architecture, that becomes very complex. If we look at just OSPF as an example, the complexity of OSPF isn't the SPF algorithm. That's a pretty simple algorithm. It's all of the coordination between databases and all of the communications and synchronization that has to happen between all of these individual control planes, and that becomes very complex, as opposed to if we take the control plane off of those individual switches, centralize it, now we have a much simpler model. I don't want to say simpler, simple, but simpler. That now each data plane is communicating just with one control plane. Visibility becomes much better. That control plane is seeing what's happening with every data plane. Resiliency becomes much faster because the control plane can recover, can recognize problems in the network much quicker and can recover from that. Just checking on my time here. So here's sort of an early model of an SDN environment. There's a couple of things that I like about this that I really wanted to point out. And that's really in this relational data store that becomes the components. I talked about network abstractions earlier and network models. You can see some of that here. We have a model up here in this SDN environment of the topology rather than the actual physical topology down there. We have service models and element models, and we have service demands. All of that gets coordinated and then pushed down to the actual physical network. But we're working from an abstraction, from a model. The other part that's really important to notice about this is the API at the top, maybe APIs, that integrate into an orchestration layer. What that gives us is an established orchestration procedure. Again, this is kind of this is a data center centric view, but this can extend out to enterprise and service provider networks. But for some time now, we've used orchestration to virtualize our storage and compute in data centers. And what SDN allows is to also bring the network into that same orchestration layer. So now, as we virtualize things, our orchestration layer can communicate through SDN to our networks and say, I need to now set a policy so that certain traffic flows from point A to point B. So the real key to SDN, just like bare metal was there for Capex savings, SDN is really all about OpEx. And some of the qualities you can see here, you have a single pane of glass control, kind of a bit of a marketing buzzword there, but it's really saying that we're touching our network just in one place. If we need to do modifications to our network, we don't have to go to each individual device and reconfigure that device. We do it once, everything is pushed down to the network. OpEx is reduced because each operator in the network can control a large number of devices. We can do zero-touch provisioning. Basically, this goes back to that earlier model with the spine and leaf that you saw. As you add new devices into the network, those devices can use there's an open chunk of software that you can load into devices called ONI, Open Network Installation Environment, that will actually go out and look for the SDN controller and download that software. You don't have to go to that switch and configure it individually. It figures out its own operating system. Programmability and automation I've already talked about. Integration with orchestration I've talked about. And of course, reducing human error. And then also, this is more of a Capex thing, even though it's SDN, there is much better utilization of network resources. This kind of goes into the whole idea of visibility, circling back to that earlier topic, that the more you can see what's going on in your network, the more you can utilize your network. Google has a great presentation. You can find it on YouTube from Urs Hosley. I can never say his name right. But what they've been doing for a long time is in the WAN between their data centers. They've been using SDN in the WAN to push link utilization almost up to 100%. That's significant because usually, because we don't have good visibility, standard wisdom is don't utilize more than 50% of your bandwidth on redundant links so that if a link fails, all of that bandwidth doesn't overwhelm, when it fails over to another link, doesn't overwhelm that link. But if you have good visibility into what's there, you can push that utilization out much further. So what does any of that have to do with IPv6? This is an IPv6 conference, and some questions here, some of the difference. I can sort of make that whole pitch about how bare metal saves you Capex, SDN saves you OpEx. None of that's really true with IPv6. Nobody really wants to deploy that because there's not an immediate return on investment. This is an expense, tends to be risky in a network, but it is inevitable. We can't go back in IPv4. IPv6 is really the only way forward. And IPv6 is really a resource issue. Service providers, for the most part, as I mentioned, are ready. Content providers need to start being ready. Data centers in particular, whether enterprise or commercial content providers or whatever, need to be IPv6 ready because of what service providers are doing. Because more and more traffic is going to start coming into that data center via IPv6, or as the other choice, through some kind of translation mechanism, which puts a lot of complexity into the network. One of the things I do want to say, just kind of as an aside there, is from my own experience, IPv6 is a lot easier than IPv4 to work with. People tend to look at those big hexadecimal addresses and be intimidated by them. The more you work with them, the more you start realizing these are actually pretty easy to work with. There's also the fact that you do away with complexities that are necessary in IPv4, like variable length subnet masking and that sort of thing. And you simplify some of the operations of your network. The question, though, is what I said in the beginning, are these are things that fundamentally change the way we build networks. Well, is that really true of IPv6? Because it is just an address. It routes the same as IPv4. You use them kind of the same way you do as IPv4. But is it important? And my answer is yes, and I'll talk about why. The other questions are, well, is SDN useful for deploying IPv6? And conversely, is IPv6 useful for moving SDN along? And answer in both of those is yes. This is something that I've been using for years. It's a graph. You can find it right out on the internet. I pulled this one up, I think 2 days ago. And what it is Google graphing out what they're seeing as far as IPv6 traffic coming in to their data centers. Every time I've used this, people will look and say, well, gee, if I presented this at the end of 2012, they would say, well, that's 1% of traffic. That's trivial. You can look right now, and it says, that's 6.3% of traffic. That's trivial. But what's important is to look at this curve. That between or through 2011, this traffic grew about 0.25%. 2012, it grew about 0.5%. 2013, it's growing about 1.5%. 2014, it's grown about 3%. Already in 2015, we've seen about a 1% growth just in the first quarter, which, if that holds, it means we'll see about 4% growth across the full year. So what's happening is that growth is accelerating. And that is extremely significant for us. If we look at just IPv4, the question becomes, well, where does that break? The pressure right now is not so much people, the number of users, even though the number of users has exceeded the number of available addresses in the IPv4 address space. What's really important are the number of things. Each person now has multiple networked devices, and this goes into that whole Internet of Things. And that is the real pressure here. And what's interesting is, I've labeled IPv4 as places rather than things. And the reason is because of the kinds of abstractions and distortions we've had to make on IPv4 addresses just to keep IPv4 networks going over the years. Between two devices, you may have, translated networks, you may have, reused networks, or addresses, I should say, and so forth. So that becomes, difficult if you're trying to address individual things and you're trying to set up individual traffic policies for machine-to-machine traffic, machine to data center, whatever, for the demands of that particular thing. You might think, I don't know, maybe I'm pushing the analogy too much here, but you might think of IPv6 as open addressing. You get a lot of the same kinds of advantages you do with open software, open hardware, and so forth with IPv6. It becomes a lot easier to adapt to your network. Because of time, I'm going to move right past this. I'd like to still have room for a few questions here, but this is a drawing that I did for a Network World article I did about 2 weeks ago that actually depicts Facebook's new architecture. And really the message behind this, it sort of goes a little bit into the bare metal message, but it goes into IPv6 too, is that what we're seeing in trends in the data center and just beginning in wide area networks, in enterprise networks, are building with smaller switches and building much flatter, much broader networks. This starts putting a lot of pressure on the address space. And, so this is part of a factor for IPv4. But there's more. What about SDN as an IPv6 deployment tool? This is a model, and sorry that I clipped this from somewhere and it's kind of blurry, but this is a model that's been developed by Huawei. And what they're doing is saying instead of having to statically set up transition tools for IPv6, we can use SDN, and they've applied SDN principles. So you have kind of an IPv6 transition service. And now it actually, through SDN, you go out and you examine what device is needing to reach what destination, and what's the best transition technology to use there. Is it some kind of a tunnel? Is it DS Lite? Is it NAT 444? And using SDN, they can actually deploy that particular transition technology for specific devices. Another interesting model, and this goes into the idea of Internet for Things, or Internet of Things. Does IPv6 support SDN deployment? This comes from Ericsson. And if you look here, what they're looking at is more their wireless network all the way into data centers at the bottom. But again, here's that abstraction and virtualization. They're taking models of the actual physical network and then pushing that up into network control. And what's most important here is this cross-domain orchestration. And at the top, we have different kinds of things, medical services, entertainment, metering, automotive services, online shopping, and so forth. And all of that is working through an API to coordinate through the orchestration layer to the actual physical network and deploying services and policies for the demands of these individual kinds of services. Last example here is SDN and IPv6 supporting Internet of Things. This comes from an academic paper that I read not long ago that actually proposes an Internet of Things agent in each device, each quote-unquote thing, whatever that thing may be, that is speaking directly to an Internet of Things controller. The controller, in turn, is working through SDN to configure the network. So we're actually setting up policies for individual traffic flows across the network using SDN, and using IPv6 so that we have exact identification of individual objects in the network. IPv6 becomes essential for this kind of Internet of Things model. In summary, I'm not going to read through all of these, but open switches are really all about Capex savings. SDN is all about OpEx, and IPv6 is really the key building block below that, especially for SDN, for allowing us to get to the kind of environment where SDN can control individual devices and the policies for those devices going across the network. So we've got a few minutes left here. I want to open up for questions. Yes, sir.
Actually, 3 quick questions. Thank you. 3 quick questions. One is in the past. So about 15 years ago, John Strassner invented directory-enabled networking, and that moved into policy-based network management. And there was a continuum developed that I think applies to SDN. Is that connected somehow, is the question?
I think it is. The question, just to repeat it for the people that are online, is about 15 years ago, correct me if I'm not restating your question right, there was a lot of work even then about policy-directed networking and administration, and is that influencing what we have with SDN now? And my answer is, yeah, I think there is very much a heritage across there. I mean, SDN itself seems kind of new, really coming out of academic work done at Stanford University that then moved into places like Google and Amazon, and they were the ones that first realized how they could improve the OpEx of their networks using SDN and better control of their network. But all of that heritage goes back to the idea of how do I automate my network, how do I automatically set policies, and I think I mentioned it earlier on, how do I do this programmatically using an if-then-else kind of language that just tells the network, here's what I want to do under these circumstances, rather than having to manually configure the network every time I want something to change.
Right. Your second definition with the abstraction brought that to mind.
Yeah.
A current question is regarding data centers and enterprises for a business case. I think IPv4 was slow adoption because single stack is easier and less complex and not as costly as dual stack.
Yeah.
I think that same rule applies when IPv6 hits a tipping point, and so again, moving single stack IPv6, that's what Facebook's doing internally, where they're IPv6 only inside and just pushing dual stack to the edge.
Yeah, and the question, just repeated for anybody that's online, is, or maybe an observation, is that the big challenge right now in data centers, and I absolutely agree, is dual stacking everything. Where you've got and that becomes a challenge of how do I migrate to IPv6 in the data center. I don't want to have to dual stack everything where I'm using 2 different addresses, or I'm doing some kind of translation at the edge. It becomes a dual stack is very hard to manage, right? It doubles your workload. So if you look at some innovative networks like Facebook, they're actually on the inside doing IPv6 only. There is a really good presentation by a guy whose name has just gone out of my head. It's Norwegian, I want to say. If anybody knows which presentation I'm talking about, I'm sure there's.
Red Pill?
Yeah, thank you, at Red Pill, where he did exactly that. It's like his thought process was, well, I can't go back to IPv4. I've eventually got to be IPv6 only anyway, so I'm going to start that way with my data center, make my data center IPv6 only, and then I'm going to use translation at the edge, sort of just backward from what most are doing, using stateless transition. And so if I have IPv4 traffic coming in, I'm going to translate that to IPv6 into my data center, with the idea of eventually IPv4 goes away and I do away with the translators. Search out there for that, and you'll find a really good presentation about it.
Thank you.
We've got a couple of minutes left. Any other questions? Yeah, Cody.
So Jeff, I haven't played around with NSX much, but just reading up on it, first we had bare metal, we had compute and operating system, then we virtualized it. That's good. Mm-hmm. With that, now you kind of need a virtual switch. And you look at NSX, it's really cool. And I get into it. Now you have this virtual router, and there's different types of virtual routers. And now you're putting firewalls down in there. It's kind of cool until you step back and think of it. The whole concept of having this bare metal device was to provide support for an application. Are we maybe going too far where now we have what we used to call a computer that now has a hypervisor running on it, it's got a full-blown router running on it, it's got a switch running on it, it might have a firewall and a load balancer and all sorts of other things?
Yeah, so the question, just to repeat it for people online, is are we kind of going too far the other way? The particular example used is VMware's NSX. Now we've got this compute device, and we've virtualized not just workflows within that device, but we've virtualized firewalls, we've virtualized routers, we've virtualized load balancers. All of that goes into basically network function virtualization, NFV. There's another good buzzword for you. And is that going too far the other way? My thought is probably not. I think we're always going to have need for standalone hardware devices in some applications, but the more we can put everything virtualized, the easier it is to, just like we do with compute and storage workloads right now, we can also now do with network workloads and vary how the network is set up, how those traffic patterns go, and it means looking first in the data center, right now, we want to create mobility in our data centers. We want to move virtual machines. And if we do it in an extreme fashion, we've got to go to the network team and say, I need my network reconfigured in this particular way. And it might be weeks to get that done because it's a manual process, fairly manual process. Whereas now being able to virtualize that process also means we can actually change our network up to moment by moment if we need to support different flows, different applications that are changing, different demands, and being able to arbitrate between the demands of different applications and available resources on the network moment by moment. So I do think that there's certainly going, like there is with any technology transition, there's going to be a lot of ups and downs, this works, this doesn't work, and all that, and that's still discovery. But I think in the long run, that's where the trend is going, to virtualizing everything.
Thanks, Jeff.
Sorry, go ahead.
I just said thanks, Jeff.
Oh, certainly. Ed, we're a couple of minutes over, so
That's fine.
I'm going to answer quickly whatever you're going to ask.
Sure. I just wanted to get your thoughts on microservices and sort of containers and what's going on in the industry with that. Do you think anything that you discussed today sort of applies and bridges into that?
Yeah, I do. It's almost a whole different topic, and I just touched on network function virtualization and all of that. But that becomes part of the SDN challenge, and the workflow challenge right now is, I've got this flow between point A and point B, or device A and device B, but that flow needs to go through a load balancer. It needs to go through a firewall. It needs to go through maybe some kind of encryption device. And so we get this whole idea of service chaining, where we're having to push the flow through certain devices, or start to put virtualized versions of that device into the flow, east and west. And of course, that's still a data center answer, but those kinds of things will eventually start moving out into enterprise and WAN architectures also. Okay, well, I don't want to keep everybody from your break, but thank you for your time.